So to do these type of questions, number one, when there are switches, you need to redraw circuit. So you know which circuit is relevant or not. Okay? The second thing, if there's diode, then you need to figure out whether it is forward bias or whether it is reverse bias. Please use the terminology in explain question. Okay? Don't just tell me it's conducting or not conducting. Test of terminology is important in exams. You have to demonstrate I am a physics student. Okay, and I'm a good physics student. So this will mean often, whenever there is AC, you will need the voltage at the source, and we need to break our analysis up into the positive part of the cycle and negative part of the cycle. And if necessary, if during the cycle it changes behavior, then you need to break it down even further. So it's analyzing by parts. So usually, you need to break down the cycle. And especially when you have diode and you have this. So the first thing we're going to do for this question, to do the first thing, is we need to define what is the potential difference of the source. And since we've got positive part of the cycle and negative part of the cycle, I am going to give myself certain convention like I did in the GSC. Okay? So the first thing is I'm going to call the terminals of my AC A and B. Alright? So the potential difference across the source is the potential difference across AB. But I'll be even more specific. I will name it the potential difference of A with respect to B. And I call it VAB. So if it is positive, that means A is positive with respect to B. And if it is negative, it means A is negative with respect to B. Alright, so you can see the first half of the cycle. So to first draw the source, there are numbers given. Later on when I solve, I'm not going to put in the numbers because I'll just solve it generically. You can put the numbers themselves. So if I look at the source, not considering the rest, to plot a sinusoidal graph, I will need two things. I will need period and I will need the peak. So we know it's sinusoidal, so the peak is 2.5, the RMS value, multiplied by square root 2. So this one, I did it to VRMS, which is given in the question, times square root 2. And that will give me 3.5 volts. Yes? So I've got my 3.5, negative 3.5 varying. And then I need the period. So if I'm given in the question is 200 hertz, so I can find the period and it gives me 5 milliseconds. So I can draw a graph that's like this. There's a reason for me to do 2 cycles, especially in the last part, because subsequently, the circuit for the last question only stabilizes after the first cycle. Okay, so I'm going to just do 2 cycles for all. Alright, so let's look at what the question wants. The question actually wants the potential difference across the resistor. So I'm going to call it VY, VXY. Again, there's going to be VX and Vy, so it's potential at X, potential at Y, potential difference across them is Vxy. So that's potential difference across R. So let's do the first part. What happens if S1 is closed and S2 is open? So let's redraw the circuit. So if I redraw my circuit, so when S1 is closed, I will have this closing. And then, of course, this part is going to be like that. And then S2 is open. What it essentially tells me when S2 is open is this part of the circuit is redundant. So the circuit looks like this. Alright. And then now, of course, I'm going to do my analysis. I'm going to do my analysis by breaking the cycle into 2 parts and see whether it is possible and do I need to break it down further. So the first part that we do is I'm going to take the positive part of my cycle. So in part 1, what I do is I'm going to take VAB to be positive. That means A is positive with respect to B. And this is what you do. You need to decide whether it is in forward bias or reverse bias for your diode. So to gauge whether it's forward bias or reverse bias, you can, of course, label this as positive first. With respect to this, then you see that this is going to be connected to the positive end, this is negative end, and then you know that it's forward bias. Alternatively, what I like to do is I go and look for connecting paths. Okay, so I can see that for a set of charges, it can move like this, no problem. I have another set of charges that can move like this. So I'll use my finger in exams and then I'll finish it up. Okay, I have connecting path. Number 2, it tells me that my diode is forward bias. Okay? Alright, so it's forward bias, that means it's conducting, and then therefore how will the current flow? So this is like a straight conductor. Okay, and you've got 2 straight conductors, you can collapse them into one single straight conductor without resistor. Yes? And then what it does is, let's trace what the potential difference will be like. So I'm going to use my highlighter. If not, you can just label VA and VB. So this is going to be at potential of A, potential of A, potential of A, potential of A. This is potential of A, potential of A, potential of A. Everything yellow down there is potential of A. So what I have is potential of X is equals to potential of A. Yes? And then what I can do is I can change my highlighter, or you can just use your fingers. And then potential of B, potential of B, potential of B, potential of B. Alright? So it tells me potential at Y is equals to potential of B. And it simply tells me potential difference across XY is potential difference of AB. So what it means for the first half of my cycle is going to follow. Okay, and I'm going to mark out my points. That's how I draw sinusoidal graphs. I need to see preamp beforehand. And then I will draw. This is the first half of my cycle, and it repeats itself after that. Keeps repeating. Alright? And please make sure you draw and don't just anyhow sketch. Because examiners do expect you to own a ruler and use a ruler. Alright? So that gives me the first half of the cycle. What about second half of the cycle? So I'm done with the first half of the cycle. In the second half of the cycle, I'm going to take VAB, and it's going to be negative. So you can see what it means is this is negative and this is positive. You can, if you need to visualize, like a battery that's varying sinusoidally. Alright? So again, I'm going to check whether my diode is forward or reverse bias. 2 ways you can do it. From the positive end, you connect one end, you will realize this is positive, this is negative. Alternatively, this is what I like to do. I want to envision a path. So what I do is I'll take my finger, and then I'll see, and then I come here, then I'm stuck. I'm against the flow. So I immediately know I am in reverse bias if I take that path. But then I ask myself, can I take another path? Yes, I can, because I went to do this switch. So yes, even though this guy is in reverse bias, I'm going to just change over. So this is like an open switch. But my current can flow like this and say, no worries, I found another way to go back. Okay? And I have this. I still have a connecting path. Alright? So, number 2, yes, diode is reverse bias. Reverse bias. Okay. But, in the end, I still have a connecting path. And then, what I have is I still have VA, Vx being equals to VA, and I still have Vy like this, and I still have Vy equals to VB, and again I still have Vxy equals to VAB. Now VAB is negative, so again it follows this part of the cycle, and then I can connect up. I will have no problem, I will still have this. Then of course you can transfer the values over for the peaks. Okay? Yes, because VAB is negative, so I follow exactly negative. Alright? Alright, so next one. What happened? S1 is open, S2 is closed. Okay, let's go fast on this one, because this one will be your half-wave rectified curve if you do this. So S1 is open, so I'll keep it open. So this guy is dead, forget this guy. This guy is dead, forget this guy. Okay? And then S2 is also open. So S2 is also open, so this part of the circuit is redundant. This part of the circuit is also redundant. And this is my classic rectification circuit. So for those of you who are sleeping in GST or couldn't quite understand, this is the next time I'm going to do the half-wave rectification circuit. Okay, so again, the analysis goes like this. Break it down, redraw the circuit, break it down into two parts, and check whether your diodes are positive, are forward bias or reverse bias. Okay, so first one, in this part of the cycle, A is positive with respect to B. So this tells me this is positive, this is negative. It's behaving like a battery like this that's moving sinusoidally. Okay, and then what I have in that sense, when I consider when VAB is positive, is I'll consider whether the diode is positive is forward bias or reverse bias. So if I follow, my diode is forward bias. Or alternatively, if I take out my fingers in exams, I'm able to find a connecting path. So diode is forward bias. And again, we can trace the potential difference. This is VA. So this is VA. This is VA, 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 VA. So potential difference, potential of A is equals to potential of X. Similarly, I can do the other one. This is, when you connect this, you'll also be able to see that the potential of B is equals to potential of Y, and in all, potential difference across XY is potential difference across AB. So for the first part of the cycle, no problem. If I am drawing VXY, which is my VR, then what I have is, it follows exactly the shape of the graph. I will have something like this. Okay? All right. So let's move to the second part of the cycle. In the second part of the cycle, I have VAB being negative. So it's this second half of the cycle that I am looking at, the negative portion. So this portion I'm looking at. Okay? So again, I repeat my trick. Now, let's label this. This is negative. Negative with respect to this. So it's behaving like this, varying sinusoidally. Alright? Now, so if I take out my finger, I do a connecting path, I'm stuck. Okay? My diode seems to be in reverse bias. Can I move up? Also stuck. So I don't have a closed path, there is no current flow. Okay? So what's the logic in explanation? Number 2, my diode is in reverse bias. And then, therefore, there's no connecting path, correct? Current in the circuit is 0 for the whole circuit. And when the current in the circuit is 0, if you try to measure the potential difference across X, it's going to behave like that. Remember? So what I do is, this is going to have resistor, and then this is the source, and then it's like an open circuit like this. And then what I have is, I try to measure the potential difference or display it across the CRO. Remember, your CRO is nothing more than a voltmeter that shows you how the voltage varies with respect to time. Okay? And then this will tell you this is going to be 0. So the potential difference across my XY, which is my potential difference across the R, is 0. Alright? And then this part is flat up. Okay? I forgot to check whether I recorded the voice. That was what happened last lesson. Never mind. You go and digest and try and do it yourself. So this part is half-wave rectification. Okay? I think the most difficult one is this one. And actually, I need 3 diagrams. I'm going to copy this guy. Copy and paste. Yes, happy. I'm going to tell you why I need 3 guys. Because I did this question already. Then I know I need 3 guys. Alright, so S1 is open, S2 is closed. So S1 is open, I'm going to just keep it open. S2 is now closed. The interesting is this guy is closed, this guy is closed, this guy is closed. Okay? And then, therefore, we start our analysis as before. Again, you realize after I redraw, then we have the following things. Number 1, what happens when VAB is positive? And we're going to do part of the cycle. And I'm going to explain why. Alright? Now, in the first half of the cycle, something miraculously happens. If I look at it, number 1, my diode is forward bias. I lazy, okay? I write FB. Please don't do this in exams. I'm not the one taking the exams. I don't need my A-levels. I want to retire. So, I need you to do your due diligence, okay? Now, it's forward bias, of course. We can trace how the current flows. Current is very interesting because when it is forward bias, like this, and very sinusoidally, in the first half of the cycle, you will realize, hey, at this junction, I got 2 paths. I can go and deposit some charges inside the capacitor. I can also pass through the resistor. So what will happen is your capacitor will try and match the potential difference externally. And to do so, remember capacitance is fixed, dependent only on dimensions. What it will do is it will charge itself up happily. Okay? So it's like I'm going to store charges. Okay? Alright, in case I need it. So I'm going to, as I charge myself up, my potential difference will match with it. This is the first half of the cycle. So what happens to the capacitor? Capacitor charges up. And the potential difference across the capacitor, it will try to match the potential difference across the resistor. Okay, as it charges up, and that will be equals to the V of the source, which is your VAB. And with that, my first half of the cycle in this part is this part. Something happens when my stores say, I got no more strength already. I need to rest for a while. Okay, now the capacitor will try to match. But you're no longer charging it up. I'm actually stronger than you. It's like connecting a 2-volt cell with a 1.5 volt cell in parallel. Okay, one of your battery gets depleted, the other one will step up to try and pump more current to maintain that 2 volt across. Okay, so during the next part of the cycle, we are still at VAB positive. But this is when T equals to T over 4 to T equals to T over 2. Something happens. The diode is still forward bias. But what will happen is that my potential difference across my cell is going to fall below 3.5, but I was charged up to 3.5. The capacitor was charged up to 3.5. So the capacitor will start discharging itself to try and maintain that current. So the actual current flow will look like this. I will still try and do this because I'm still forward biased. But hey, the capacitor tell the source, you're too weak already. I need to step in and maintain. So I will start discharging myself. But in the process, as I discharge myself, I also get weaker because my charges will come out, my voltage will start to fall. And it's a discharging through a resistor. So this part will also flow. So if this is I1, this is I2, then this is I1 plus I2. And it will try and maintain across the resistor of that 3.5, but it will take the bigger of the two capacitance. So this is the part of the cycle that's big, a bit different. Your capacitor start to discharge. To maintain, to try and maintain. Try only, try and maintain the voltage. Okay, so the overall potential difference across XY will be the potential across C. Okay, and it follows it. So at this point in time now, what will happen to the capacitor of the potential difference across the capacitor? It will start to discharge exponentially. Okay, so this is why you have this part of the graph. Alright, so this is for part 2. So this is for part 1. Now, then we have the fun part, because the next part of the cycle is negative part. Okay, so we are focusing now on this part of the cycle, the negative part. Alright, this one very easy. So if I redraw the circuit, negative part, this is negative. Oh, this is negative with respect to this guy. So it's functioning like a battery that's like that. And if I trace, this is positive, this is negative. And if I trace the current, oh, cannot. Against valve. Then I try and trace the current, also cannot. Correct. So your whole part of the circuit, this whole part, let me see if I can do purple. Okay. This part of the circuit, ayo, no use lah, you. Okay? You are redundant. Because there's no connecting path to this part. So basically, you only focus on this part of the circuit. And what happens? Suppose I still have charges left. This is in the case I still have charges left. Now I really need to kick in and play my role. Okay? And then therefore I will continue to discharge. So let's finish our story here. So in part 3, let me write down the key ideas. Your potential difference across AB is negative. But what happens is your diode is in forward bias. This means your source cannot charge capacitor, and there is no current from source.
Diode is in the forward bias, sorry.
Oh, it's in reverse bias. Thank you. And so what the capacitor has to do? The capacitor continues to discharge. And then the potential difference, so it's like your discharging circuit. Okay, so it's similar to this. This is your capacitor, this is your resistor, and it continues to discharge. And then, therefore, potential difference across the capacitor matches the potential difference across the resistor. And I will continue to discharge. Come. How much to discharge to? The first question is, do I discharge before I finish the cycle, or how high do I go to? This is the part that is not in the solution I gave you. I went back and we looked at the mark scheme. They do mark one additional point for this. Because there are numbers, there is a time constant. What's the time constant? Come.
CR.
Yes. And if you work that out, how much was that?
5 ohms times 1 micro
Fahrenheit? No, farad. Yes?
Yes.
And what do you get? 5
micro
seconds, which is 1 whole cycle, correct? So if I consider from this point, where's the 1 cycle later here, correct? And what's the concept of RC? It decays to Q0 over E of the value, correct? Or V0 over E of the cycle. What is 1 over E? 1 over E is 0.37 approximately. So I am only left with about 37% of the original. Yes?
Isn't 5 should be 1 squared to the left, the 5 milliseconds?
No, here.
Oh, from that point. Oh, okay.
Isn't this 5
Yes,
milliseconds?
it is.
Okay? So if I start discharging from there, 37% is somewhere down here. So yes, I will still be able to discharge and it won't go to 0, and I should tend towards that point. And in fact, the markers say you should be able to find the V here. Because you know that this part is T equals to 0.75 of big T. So you can substitute into V equals to V0 E minus T over RC to work out this value to mark up. Okay, those, he says good students did that and they got an additional point. If you run out of time, of course you won't.
Would it just be V0 over E?
No. Because here, at this point it is, if you take this at T equals to 0, this is not RC. At this particular point here. This one. Let me take out my laser pointer. At this point here. This point would be V0 over E. This point is V0, but this point is not. Okay, that one is only 3/4. 3/4 of T. So you substitute inside, you should be able to get that value.
Oh, we're doing it because we're trying to finish that cycle, right?
Yes, so they did mark for that one. And then of course, once I hit until here, because I'm always stronger, correct, then I'm going to grow weaker. But now, my current comes in. I have enough rest already. I'm ready to charge it up again. So next, your source is going to take over and charge up the capacitor again. So follow this. And then after, so follow over this. And then after that, oh no, my source is weakening again, so I'll discharge again. Wait, let me try and mark out, okay?
So wouldn't it just be the same pattern?
Yes. After the first cycle, it will do this. Okay, one more extension. This is called smoothing of the AC graph and rectified AC graph. It's still not very smooth. If I want it even smoother, I don't want it to discharge so fast. So how can I discharge it even slower? What do I control? Control the RC value. Okay? Alright, so if you have R that is unchanged, because it's a appliance, you cannot change the R inside, correct? Then what you will do is you will change your C value. Okay, so the RC values, if you change your RC value, if you increase your RC value, then you will get something maybe like this. This is if you increase the RC value. Yes? Then it'll get smoother and smoother. The more you increase your C, then of course it'll get closer and closer to the top until it almost behaves like a single value DC. Can? Of course, if you match wrongly lah. Student 6A was asking me this. What happens if you go like this? Go like this, die already lor. Then you have to wait until all the way until here before it charge up again lor. Correct. This is when you decrease the RC value. Decrease the RC value. Huh? It is possible. Yes?
Because there's like two different graphs, right? One is the capacitance graph and the other one is the EC graph, right? So do you draw both in ordered lines, or do you draw like the highest EMF value as like the ordered ones, and the rest is dotted?
So the dotted one, I will do in pencil.
Oh, okay.
And then finally you label lah. Do one in one color lah. So this is the one. The bold one is the one I want. Okay, and this is my VR, which is equals to my VC also.